Alrighty, welcome back. And again, we'll be starting the webinar in just a couple of minutes. I'm just confirming and checking that everyone can hear my voice and see the screen. It sounds like everyone can, which is great. So I'll do a little bit of housekeeping as we're waiting for the last few people to log in. So my name is Dr. David Kanashko. I'm the medical director here at Biphasic Laser Therapy. We're based in Toronto, Ontario, Canada. And we've been manufacturing and supporting and using low-level laser, photobiomodulation, laser therapy. There's lots of different names for this type of light therapy for over 3 decades now. And the purpose of these webinars, I do 2 types of webinars every month. One I do more for the consumer, because we have consumer devices that are used at home, and one more for healthcare professionals. They're always complimentary. You can watch any of the ones that you want, regardless of your background. But of course, today's is geared more towards healthcare professionals, perhaps using our professional system or a healthcare professional that is interested in laser therapy and wanting to understand a little bit more about the therapy itself, how it works, and so forth. These webinars are always recorded. So if you can't watch it all in entirety, or for future reference, if you want to join in a webinar but can't, as long as you register, you'll be sent an email, a follow-up email. Usually it takes about a week to edit it and then send out that follow-up email with a link to watch it again. And alternatively, eventually they're uploaded to our website. If you go to our website, biphasiclaser.com, and click on support, you'll find an icon for webinars. There's the personal webinars and the professional webinars, and the library of the webinars are there as well, so that it will be also uploaded to that link as well too. So today's webinar, as I mentioned, is more about understanding, some of the basics of laser therapy. And I say that in a way that it sounds basic, but there's still a lot we don't know, and we do know a lot. And sometimes it's misconstrued or not really understood properly. Sometimes there's misinformation, to put it kindly, that has been put out there. So what I'm trying to do today is clarify and clear up some of the misconceptions and/or verify some of the facts that we know of, and also some interesting things that perhaps we need to do more research on and understand how to have better clinical effects. Hello, Tickle there. So what I'm going to do today, by the way, if you want to ask me a question, I encourage you to do that. I will definitely get to those questions at the very end of today's session. So type it into the Q&A box, and not to the chat form, because I can't manage both. At the end of the day, I just go to the Q&A box, and you can type them in as we go along, and then I'll answer your questions. So I wanted to start off with talking a little bit about a historical perspective of photobiomodulation therapy, and then get into the main researcher that started a lot of the understanding of the mechanisms, which it turned out to have a better understanding of wavelengths, and that's Tina Karu. I'll explain her work. And then I'll get into the mechanisms of photobiomodulation, and specifically what wavelengths seem to be effective, and perhaps even some promising wavelengths that are starting to be used both in research, and we're starting to see them in clinical applications as well. I'll talk a little bit about how this light goes into your body, so sometimes referred to as a penetration, and how that relates to the wavelengths as well. And then I'll get into understanding a little bit more about dosaging, which is really critical to get a good response from your patient. And this is probably the most important aspect of what I'm going to talk about today, as well as something called a biphasic dose response, so you can clearly understand what it is you're trying to accomplish and why you may or may not be getting good results with each and every patient, or yourself, or depending who you're treating. Then I'll do a little summary of takeaways, and I'll have time for Q&A. So that's kind of how the the session will go. So historically, many of you are aware, especially if you watch some of our webinars, where this photobiomodulation first came about. And the reason why I'm going to rehash this is because historically, Andre Mester, who was starting to do laser research back in 1965, and that was just 5 years after the first laser was developed. That laser happened to be a ruby crystal laser, and the wavelength was 695 nanometers or red. So it just so happened that this wavelength proved to be quite important in the discovery of photostimulation, and eventually, we refer to as photobiomodulation. So Mester attempted to use a high-power ruby laser to destroy malignant tumors. I think many of you are aware of that. You can sort of see at the bottom here what that laser looked like. It was quite large. You can see sort of the red crystal rod, and there's a fluorescent tube wrapped around it. That's how it was energized. And so to his surprise, when he was trying to do these experiments, the tumor cells were not destroyed by what he thought was going to be high-powered laser therapy. Instead, it was observed that in many of the cases, the incisions made to implant the abnormal cells appear to heal faster in the treated animals. And so he basically found that for whatever reason, this red light was actually helping these incisions heal, not necessarily thermally deactivating the tumor cells. So he carried out further experiments. And again, I know I don't want to rehash this. Many of you have watched this type of the experiments before in my past webinars, but I do want to mention that he carried out many different experiments, including on skin defects, which is what you're seeing here, burns, and human cases of ulcers, typically from diabetes, venous insufficiency, and infected wounds. And he was finding that they were all healing faster in response to this low-powered red light. Now, the first commercially available lasers weren't this ruby crystal laser. They were very bulky and kind of not commercially viable. They developed a laser called a helium neon laser, using helium and neon as a substrate, or called the lasing material. And the initial wavelengths that were derived from helium neon were infrared or near infrared, around 1152 nanometers. But because these were invisible, the applications, the commercial applications weren't really good because you couldn't see the beam, right? So another manufacturer and some people were involved with developing a visible spectrum helium neon laser. And that ended up being in the red wavelength, or 633 nanometers. So this had much better commercial applications. Mainly, you can imagine when you have a visible beam, you can use it for surveying, construction, all sorts of different, especially construction applications kind of scenario, but also other types of applications, including surgery and eye surgery. They were using high-powered red lasers for that. So because of the widespread availability of these red wavelengths, again, we didn't know really a lot about red, but they were starting to be used for medical research, including early laser therapy or photobiomodulation applications, and mostly with wound healing. Those were the first kind of historical uses of this red helium neon lasers. So now let's fast forward to Tina Karu. Tina Karu is an Estonian researcher. She is well decorated, PhDs and all sorts of different, educational background. And she was a biophysicist, and she was, at the time, this was the Soviet Union, Estonia, and so forth. She did her training in Moscow University. And she started to explore the mechanisms of laser biostimulation. And the reason why probably she got involved was that Mester was Hungarian, and Hungary was under the sphere of influence of the Soviet Union. So this type of phenomenon was starting to be applied and used clinically early on by the Soviet Union. And so that's where you start to see a lot more of the research. It was very slow to catch on in the Western world, you might say. So she was active in the 80s and 90s and 2000s, and really up until pretty recently, she was doing research and writing papers. I think she's retired now. We had an association with her. We have a lot of Russian-speaking employees here at Bioflex, and back in the day, even Fred Kahn had communications with Tina Karu about her research and wavelengths and what might be applicable for clinical use of lasers. And she's even spoke at some of our events, and so we knew her quite well. Now, she explored something called the action spectrum of cytochrome C oxidase, which is a terminal enzyme of the electron transport chain that's responsible for oxygen reduction and ATP production. So to understand, an action spectrum is essentially a plot of relative effectiveness of different wavelengths of light causing a particular biological response, and under ideal conditions should mimic the absorption spectrum of the molecule that is absorbing light. And essentially, this will cause a photochemical alteration. So that's a lot of science jargon for the concept of light causing a photochemical reaction. Now, the action spectrum in the visible to near infrared region measured for biological responses of cultured cells showed that red light, that historically was used, everyone was using red light because that's what was available. She found that that was not the only wavelength suitable for this laser biostimulation due to her research. So she really focused in on the action spectrum of what she thought was one of the main enzymes responsible for this phenomenon of accelerated wound healing and other applications. And so by doing these experiments, and there's quite a lot of them that she did over the years, she discovered there's a range of wavelengths that are best stimulate this enzyme that seems to propagate photobiomodulation. And in the far red range, it's a range. It's not a specific wavelength. So anyone that says one exact wavelength is it, that's not really accurate. You can use a range if you're in. You can use different wavelengths as long as you're kind of in this range to be effective. I turn on my buzzers here. Sorry, guys. So I should have turned all that off earlier. And also 2 near infrared bands as well. So red was around 667 to 683 or 684, and in near infrared 750-ish to 772 and 812-ish to 846. So in these ranges, she found had the most stimulatory effect on this cytochrome C oxidase. So I want you to pay attention to this graph, and it's quite interesting. So what you're seeing here at the bottom is quite clear, is wavelengths, right? 600, 700, 800, 900, 1,000 nanometers. Just to refresh your memory, red is in the low 600s to the high 600s. That's sort of red wavelength. And then as you get above 700, you're entering the near infrared wavelength, and then you get into mid infrared and far infrared, which is well over thousands of nanometers. So what she found was that the relative absorption or the activity of the cytochrome C oxidase, you can see the cytochrome C oxidase are the little black dots that are connected. You can see they're most stimulated in and around, if you sort of chart down, around 650, 660 nanometers, right? You can see here that it's quite stimulated. Then it starts to drop down into the bottoms out around 700. And then it starts to peak up again in the 800s, and then it starts to peak down again. Now, if you look at what she's looking at, which is ATP content, meaning the more ATP, the more activity, as well as cytochrome oxidase activity. And you can see here, it's quite high in the red. So ATP is increased in the red. Cytochrome C oxidase, which makes sense, is increased in the red. It dips down in the low 700s, and then it picks up again and peaks out again. ATP production, not quite as good as red, but still pretty good around that mid 800-ish nanometer range. So it was this work that she established these ranges of wavelengths that really should be used in photobiomodulation. And I'm going to talk a little bit about some other wavelengths that are up and coming and interesting. But if you're choosing equipment and you're not using these wavelengths and you're trying to achieve photobiomodulation, number one is I question what you're trying to do. Number two is that it's not following the science. So we need to understand that as well. So this particular diagram basically shows you what's going on here. When you have, now HV is light energy, right? 600 to 900 nanometers, in that range that I just mentioned. The light will penetrate into the cells. It will be absorbed specifically by cytochrome C oxidase, right? As I mentioned. And what happens essentially is you get an increase in ATP, you get releases of nitric oxide, which can be a secondary messenger, and you get a short spike, and I'm going to talk about this, of reactive oxygen species. These are free radicals that in small concentrations, when they peak, they will stimulate certain enzymes, including NF-kappa beta or nuclear factor kappa beta enzyme. And this leads to transcription of cellular proteins that help protect the cell against further damage. So we're talking about cells that are inflamed, injured, diseased. These are the kinds of cells that respond extremely well. I always get this question as well. Well, what about normal cells? Well, photobiomodulation doesn't really do much to normal cells. And that's for the fact that there's no real, the acceptors for the light aren't really there because of the mechanism. So in other words, the light's absorbed and breaks hydrogen bonds of nitric oxide bound to copper or iron. In normal, regular, healthy metabolic cells, that doesn't really exist to any great degree. So when you photobiomodulate normal healthy cells, you're not really altering any of the metabolism because it's not being absorbed by that specific target, because it's not there because of the lack of nitric oxide or the lower amounts of nitric oxide. So this is kind of what I'm referring to. So this is cytochrome C oxidase. And I know I'm getting a little bit of detail, but it's quite important to understand that as the light's coming in, it's actually being absorbed by nitric oxide that's bound. You see it where it says NO, and then it says CUA. So what happens is nitric oxide in high concentrations, and this is because in inflammation, you have a buildup of intracellular nitric oxide. It binds to these copper subunits and essentially blocks. You can see this red X here. It blocks oxygen from binding to the iron substrate, which means that now you have inhibition of cytochrome C oxidase. It acts as a poison, you might say, for the ability of cells to produce ATP. When the light comes in, it can break the bond between nitric oxide and copper and iron subunits, causing it to be released. That's what this little arrows show here, allowing oxygen to bind back to its normal substrate, copper or iron, and then allowing for the ATP production to occur. So in another way, as light is entering into the cell, it's interacting with these different areas to allow for an increase in respiration rate or ATP production. So what's really interesting here is that, I'm talking about 600-ish, 620, 630, up to 850, and these peaks that we've talked about. When you use those wavelengths, we're understanding that this is the mechanism that I've mentioned about ROS and nuclear kappa beta factor and the release of nitric oxide. All these things can start to occur. But they're finding that other wavelengths, specifically I'm going to focus in on a little bit farther infrared, and that's around 980 nanometers. Here it says 900 to 1100, but in that range, especially around 980, seems to have an effect on what's called heat light gated ion channels, which allows for calcium to flow into and out of a cell. And it provides calcium signaling, which can create a lot of positive effects inside the cell. So we're finding that that other wavelengths seem to be absorbed by water in different conformations that changes the physical structure of these ion channels that seem to have an effect on the cell as well. This is independent of the mechanism of ATP production. So I think what you'll be finding in the near future is that we'll be using other wavelengths, not just 660 and 830, 840 nanometers. That's what we use in BioFlex. But we may also start to use 980 nanometers and maybe some other wavelengths that, as the research is showing that it can be clinically effective, we need to understand the dosaging. But you can see that this may also have a positive effect on photobiomodulation. So let me draw your attention to this particular paper, in part written by Michael Hamlin. Many of you know Michael Hamlin. Excuse me, he's retired now, but he's considered the leading expert in photobiomodulation mechanisms, has done a tremendous amount of work, especially in the neurological aspect. And in this particular paper, even though they're talking more about pulsing and perhaps the importance of pulsing, but they also talk a little bit about the fact that what governs the depth of penetration. And really, the main thing here is the wavelength. That's what seems to govern the ability of light to go into the cell. Now, believe it or not, the problem is your skin, right? So most light is absorbed, scattered, reflected because of the skin. And all the different photoacceptors or chromophores in the skin prevent light from going very deep or reflected off or scattered or what have you. And that's one of the key things that I always harp upon if you're trying to do laser therapy, is that almost all clinical trials and research, and certainly what we recommend as well, use what's called a direct contact. And that is the diode is close to the skin as possible, touches the skin, and pushes into the skin or the tissue to allow for the light to actually penetrate a little bit deeper down into the tissue, not because of the wavelength, but because you can mechanically push the tissue down to allow the light diode to get closer to your target. This may or may not be important depending on what exactly you're trying to do with the light. For a lot of applications, you don't need to worry about depth, but for other applications, you do. And there's lots of other factors like, are you trying to penetrate through bone or tendon or muscle? The amount of melanin or skin color, the amount of blood perfusing. In fact, there's some research showing that if you use a cold compress before you do photobiomodulation, you can actually achieve a greater depth of penetration. And of course, if there's hair in the way and the color of the hair might be problematic as well. And the amount of adipose or fat tissue may also affect the ability of light to penetrate. This chart, which many of you may or may not have seen before, shows you the absorption, the percentage of absorption by different wavelengths and by different photoacceptors, including water, which is that gray area, melanin, which is the blue dots, and hemoglobin in blood. And you can clearly see here that if you look at melanin, it highly absorbs light in the 400, so that's a UV range, and then starts to peak in the beginning of the red, and then starts to die down into the red and near infrared, right? So if you use a wavelength in the blue or violet or ultraviolet, it's not going to penetrate very deeply, or even orange, and that's because it's being absorbed almost a lot by, well, that's not a good way to grammar, but it's being absorbed mostly by the melanin in your skin. And if you look at water absorption, same kind of scenario, you can see that water absorbs a lot of light in the wavelengths as you get closer to 1,000 nanometers. And then it sort of has a little dip and then continues to absorb lots of light. So traditionally, lasers that have longer wavelengths, like over 1,000, they're absorbed by water molecules and they heat them up. And that's usually how surgical lasers or class 4 lasers are used to heat up tissue. And then hemoglobin, same thing. You can see it absorbs lots of wavelengths up until around 600, then radically drops off because it reflects red, right? Which is why it appears red. And so that's in part the basis of why certain wavelengths are used as well, because you want to avoid absorption by these other photoacceptors. So there's been lots of research done to look at, what wavelengths would potentially go deeper. This particular paper concluded that the low 800 nanometers achieved around 3.5 centimeters depth of penetration. And when they used a higher wavelength like 980, it didn't go as deep. So that doesn't necessarily mean you shouldn't be using 980, because as I mentioned earlier, it might actually have some good benefits. It's just that it's not necessarily going to go as deep as well. So you need to understand that. So the most transparent wavelength tends to be this near infrared around the low 800 nanometers. This next paper, in part by Juanita Anders, looked to observe the transmission of continuous wave 810 nanometers in light, a wavelength of light, comparing that to 904 superpulse wavelength as well, and through skin and gastrocnemius tissue. And so what she found was that the 808, or the near infrared, penetrated a percentage of 25% approximately, compared to 20% in skin and muscle. So basically what she concluded was that 810 nanometers can actually go deeper than 904. And again, 904 is used in research, and it's not necessarily a terrible wavelength to use. It's just that the claims of it going deeper, unfortunately, aren't accurate based on research like this. So as a reminder, when we talk about dosaging, we're talking about some parameters that you need to be aware of. First of all, you have the power of your light. It could be a laser diode, it could be a bunch of LEDs. Typically, you're going to convert it to watts. Usually it's in milliwatts, but you want to convert it to watts. And then you want to multiply it by how long you're treating for to get the number of joules of energy, which is a good sort of dosaging point, except that one needs to understand that you also need to take into consideration the surface area that you're treating. So for example, if I have 180 milliwatts, that's roughly what our laser probe is, multiply it for 10 seconds, you have about 1.8 joules at that one point for 10 seconds for accumulation. Now, if I now divide it by the surface area, our surface area is approximately 0.1 centimeters, but again, there's a bit of variability there, but for the sake of argument, that ends up being about 18 joules per centimeter squared. And that's referred to as the energy density, which is really considered to be the most accurate form of dosaging parameter in photobiomodulation. So, it's funny, I actually am using a different format today for the PowerPoint. You can see I'm kind of, in the background here, unlike the normal one I've done in the past. And it doesn't allow me to use all the capability of my PowerPoint because I had all these coming in at different times. But what I want to show you here is that, let's say you're using 820 nanometers or 830 nanometers at the surface of the skin. The depth of that light is, as I mentioned, the most transparent. And let's say it goes 4 centimeters, which is that bottom line. Okay, so great. You can say this light is going to 4 centimeters. The problem is, when you talk about dosaging, it's measured at the skin. The amount of light that's actually makes its way, so I'm talking about photons, that makes its way to that depth, set, say 4 centimeters, is much less, obviously, than closer to the surface. So even though you might say, oh, great, you know, my laser can go to such and such a depth of penetration, unless you have enough light to trigger a response, it's not doing anything. It's like you don't have enough dosage to do anything. So to counteract that, you can do one of two things. You can increase the treatment time, which we're going to talk about, or you can increase the power. Now, increasing the power makes a lot of sense, except that once you get to be too much power, it can start to burn. So you're limited how much power you can use. What you don't want to do is cause heating. Heating is not the effect you're looking for. You're looking for a photochemical effect, which is independent of heat, essentially. Okay? So when you're doing photobiomodulation therapy, one needs to understand is how deep do you want your light to go? Is it feasible? And also, how should you be adjusting your parameters in your equipment to get the best clinical response? This particular paper is an update by Michael Hamblin and some other authors, and basically talking a little bit about the biphasic dose response. So many of you are aware, I've talked about this before, this Arndt-Schultz curve or the biphasic dose response. Essentially, you have the strength of the stimulus, and then you have the reaction on the vertical axis. You know, from A to B, there's not much going on because you don't really have enough stimulus to cause a reaction. But then as you start to increase your stimulus, you get a reaction, and eventually you get an optimal reaction. But then if you start to increase the stimulus, you start to get decreasing reaction, and then eventually you get inhibition. And Hamblin and these authors kind of explained why this is occurring. So if I'm going to do my best to try and explain that. So first of all, for photobiomodulation to take place, there has to be enough dosage, right, in order for this reaction to occur. And this depends in part on the optical properties of the body tissues, like I've explained, and the wavelength. So even though knowing the correct wavelengths, the skin is still definitely the biggest barrier to effective photobiomodulation treatment. It blocks out most of the incident energy, again, by scattering, absorption, and so forth. So therefore, the energy dosage for the deeper parts of the body remains at that far left of the curve. In other words, you're getting very little light or dosaging to the deeper parts of the body. But that isn't necessarily a bad thing. You just may have to increase your treatment time. So here's a classic example. This is from that paper that I've just referenced by Hamblin. Not his paper, but he was referencing another paper. Now, I'm going to explain this. Essentially, what they were doing here is they were looking at the dosage, joules per centimeter squared, and then they were looking at the effect on wound healing. Now, they used 4 milliwatts per centimeter squared. That's the power density. Okay, that doesn't take into effect time. Then they started to see the different periods of time and what kind of effect that had. So in other words, same power, didn't alter the power, they just changed the time, and they observed the effect on wound healing. So this first one represents 1 joule per centimeter squared. So that was for 249 seconds. And you can see they got this result here. Then when they doubled the time, they got a significantly better healing effect of the wound. And then following the Arndt-Schultz curve, as they start to increase the time even more, and therefore the dosage, look what happened. The effect diminished. It still is pretty good compared to the 1 joule, but not as good as the 2 joules. But then is what you need to pay attention to is when they increase the time even more and more and more and more, to the point where they went from 249 seconds to 2,290 seconds, there was inhibition of wound healing. a negative effect. So the takeaway here, and it's an early takeaway, and that takeaway is you don't want to excessively treat your client. Our equipment is designed to have timing protocols, so you should never do that. But if you don't have that, or you're not quite sure and you're treating for too long or too much power, you can actually cause this inhibition. So the reason for this, they're hypothesizing, this is Hamlin and his team, is that there's two kinds of ROS, or reactive oxygen species. There's a good and a bad ROS, and that has to do with the amounts of the ROS. They're probably the same types of ROS, but good ROS tends to be connected with stimulation of the mitochondrial electron transport chain, which increases ATP. So these good or lower levels of ROS initiate beneficial cell signaling pathways, and that leads to a whole transcription factor, nuclear factor kappa beta pathway I mentioned earlier. So when you activate this, it causes the expression of proteins that help the cell proliferate and survive. Okay, that's in this sort of lower dosage. But as the fluence of light, in other words, as the energy density of light increases extensively, the beneficial RS production starts to become a negative. So when more light's delivered, there's a second peak in RS production, and this is basically what they refer to as bad ROS. Bad ROS, meaning high concentrations, damage the mitochondria, leading to the initiation of triggered cell death, exactly the opposite of what you're trying to do. So ROS, it's a whole complex understanding of this, and I won't get into it, but essentially ROS, as the concentrations peak and go too high, they trigger the cell to go, holy crap, we need to kill ourselves because this is going to have a negative effect. And that's exactly what happens. So it triggers the cells to die. So when in that example I gave of the wound healing, you can see where it inhibited, and in fact, the wound healing slowed down instead of sped up because the dosaging was too much. Now, to do this in your client is, you'd have to really be overdosing and doing it for too long. It's possible, and in fact, that may be sometimes why you're not getting the desired effect as well. But normally it's because you're not dosing enough. And that's if you're using our equipment specifically, because we always start our dosages at a particularly low level and allow you to increase those levels. So my takeaways here, I know I'm going a little bit over time, are the ranges, the most effective ranges based on the historical research shows in the far red, 670 to 680, we use 660. And in the near infrared band, 750 to 770-ish, and 812 to 846, we use 830, 840 at Bioflex. There are some promising new wavelengths. I guarantee you that 980, you'll start to see more of that, and we're definitely looking at that to incorporate in some of our equipment. The depth of penetration is a factor of wavelength. And we know for a fact that near infrared around 810 plus or minus 10, 20 nanometers is the most transparent and will penetrate the deepest. But again, you need to have enough dosage to get to where you're going. If you're treating most joints, the synovium is your target because you're trying to reduce inflammation. You don't need tons of energy to do that. But if you want to go really deep, then you need more energy at the surface of the skin. Remember, power and time are critical for optimal healing. So longer illumination times are more effective, but they have to be within that biphasic dose response. If you treat for too long, then you may be in that negative zone, or if you have too much power. So my advice is always start with lower times and power. And if the patient's not responding after several sessions, not just after one, then start to increase the time and or the power. Understand what you're trying to target. If it's relatively superficial, within a centimeter or two, and most things are, then dosaging is pretty easy to get. But if you're dealing with really deep things, deep structures like the deep hip joint, intervertebral discs, the stuff that the anatomy that's pretty deep, then you're going to have to use more power and or make sure you have good pressure on the area to displace and get the probe or the dial closer. You may not have the same results with each patient. And again, that's because skin color variability, tissue depth, tissue density variabilities. So be prepared to play around with your parameters a little bit and see what works, what doesn't work. And don't just not think. Use your thinking cap for every patient, just like you would doing another type of therapy. The protocols that we have, we know are effective for most scenarios, but you might need to tweak them a little bit. And that's called customizing the protocols, which kind of makes sense because of what the research is showing. Upcoming events, we're having a big masterclass on July 8th. If you happen to be in the area and like to join us, that is up in Newmarket area. And it's up on our website. The thing about this is it's geared towards sports injuries. That's not the only thing we're going to be discussing, but one of the biggest things we've been we've been asked about before is concussions and how to treat them. So because concussions are a big part of sports injuries, Dr. Randy Santiago, our Chief Clinical Research Director and expert in this field, including running some trials, is going to do a lecture on treating patients with post-concussion syndrome, but also doing some practical demonstrations and some workshops on this. And so the purpose of that is when you walk away from this event, you should feel like you can treat concussions, right? So that's what we'll be doing. It is in person, but we will be doing it streaming live online. What might be difficult to stream the practical sessions, but certainly the lectures will all be streamed. So if you aren't able to make it in person, I'm not sure if it's yet up on our website, but you can also join in and watch it and stream it live as well. All right, so I think you have a few questions here. So someone mentioned, hi, Marianne, that they were at a conference when Tina Karu was speaking. Yeah, she's really an incredible person as far as understanding, and we really owe her a lot to understanding exactly what's going on. Someone's mentioned that I was freezing every 2 to 3 seconds. I hope that wasn't, thanks for the feedback, Mike. I hope that wasn't the issue ongoing. Can I expand on the use of cold compress before treatment? I don't traditionally do that, but I would say this. If you're using our equipment, I would use your dual array normally. And then if you're trying to target something really deep with the laser probe after the array, you could put on, just ice it for 5-10 minutes to diminish the blood flow over the area, then use your laser probe. That will bypass some of the absorption of blood. That's what some of the research was showing. So that just might be one idea to try and get a little bit deeper with that, Marianne. Is there research on the use of PBM on cardiac angina and the effect of nitric oxide? Well, so nitric oxide has a short half-life of like 4 or 5 seconds or something. So the effects mediated by nitric oxide for photobiomodulation are transient. They don't last very long and they're localized. So it's not really going to work for something like angina, but the systemic effects of photobiomodulation have been shown to work with some issues of cardiac myopathy and post-infarction. I think I've done some presentations on that as well. Why is cold laser therapy designed as red light first, then infrared? Is it because its skin cells have more melatonin or melanin where the light is absorbed the most? So red light, even though it doesn't go very deep, is still a pretty effective wavelength and can still get to a lot of structures superficially. So it's a very good wavelength to use. It's also very good with being absorbed by the blood, especially white blood cells and stem cells, which make their way to deeper areas. So red light tends to be used as well. At least we use it. And also to perhaps the theory of stimulating photoreceptors with red light first allows, because those receptors can't be re-stimulated because they're already been triggered with the red light, the near infrared light, more of the photons can bypass those receptors and go deeper. So red and near infrared theoretically lets the light go even deeper. My slides, I don't give them out kind of scenario. You can always contact me if you'd like certain aspects of the slides. I don't mind doing that. And of course, the webinar is always recorded to watch again. What about using devices that combine several wavelengths with the same parameters? Can they be counterproductive? Devices that combine several wavelengths with the same parameters. I'm not quite sure what you mean there. I know I've seen devices where they use like, I don't know, like orange, yellow, green, blue, violet, they're all together, whatever. That's a different scenario. As I mentioned, the wavelengths that you're trying to use specifically are the red and near infrared. And those are the two wavelengths that one should be doing. And they're going to be doing similar things. It's not like red does something different than near infrared based on the mechanisms that I showed you the research by Tina Karu. It's just that how they penetrate is the main difference. If probing longer or pressing too hard on the same spot, would that negatively affect the use of light energy to the affected tissues? Not pressing hard, because you're just trying to get the light to as deep as possible. But the longer you hold the laser probe, as I mentioned, you're starting to increase the energy density. And, depending on your target, if your target is really deep, that's okay. But if your target is superficial, then you don't want to have a really high energy density, because that might not be as effective based on what I just showed you earlier about the biphasic dose response. Any studies on hydration level of the patients and treatment efficacy? Someone else asked me about that before too. No, I've never seen any research on that. I don't think there really be much to that, but who knows? Are there settings that are more beneficial for chronic versus acute? When would you use certain waveforms such as a sine or triangle wave? Yeah, so, we've actually kind of gotten away from the waveform, where the square wave seems to be the most effective. And that because it delivers all the light at one time and then drops it off. But you can try sinusoidal or triangular waves, which ramps it up and then down. It's a little bit more gentler way of bringing the light on. I don't know if it necessarily does a whole lot. Acute versus chronic. Generally speaking, we tend to go slow and low with acute issues. And for chronic, it's not uncommon that you can kind of tweak things up a little bit more to get to be more effective, if that makes sense, Joanne. Which frequency is the best? I'm not sure if you mean like the pulse rate. And if you mean the pulse rate, there's no consensus on that, other than in neurological stuff, they're using 10 hertz and 40 hertz. That seems to be effective. We use a range from as low as 10 hertz up to 250 to 500 to 1,000. As far as 10,000, we find in the range of 10 hertz to 250 to be usually the most effective. Does icing before the probe only apply to inflammatory conditions? Yeah, so I wouldn't ice a condition where the patient might be sensitive to that or not allow for it, but you can use it for chronic and acute. It really wouldn't matter. It's the purpose of that is not to affect inflammation, but to displace blood away from the area to allow light to go deeper into the tissue. I hope I made sense there. Difference between the mode, continuous or pulse. I didn't spend a lot of time on explaining that, other than most research is done with continuous wave of light coming out. We also know that when you pulse the light, it might affect how deep it goes, although there's questionable research on that. But also it affects how the light's delivered to the cells. And this might reduce the biphasic dose response. In other words, when you pulse the light, you have a greater flexibility before you become inhibitory. And that's because the light, instead of all building up at one time, is being pulsed. So you have light, dark, light, dark, light, dark, and therefore you sort of stagger how that light's entering the cell, causing the reaction, so it might not build up as much. And that's the purpose of probably pulsing, although we still don't know a lot about it. Hi, Dr. Heaviside, hope you're doing well. When will this talk be posted and will we receive a link? I think I covered that earlier. You will definitely get a link to it. Let's see here. How many sessions can we give to a patient? Is there any harm if we use laser for a long time or too many sessions? I can say this is that the traditional treatment plan is every other day in a clinical setting. So, you know, Monday, Wednesday, Friday, or what have you. Sometimes we'll do 2, 3, 4, 5 days in a row if it's really acute, or if there's an really bad wound we're trying to heal, or what have you. But usually it's done every other day. At home, for consumer devices, usually the power is not as much. Sometimes you can get away with treating a little bit more, but you do need the body's time to recover and do what it's trying to do too. So you don't want to overstimulate, especially treating too many times in a day as well. Too, usually it's once a day that we'd recommend. I think you try to avoid the use of red and infrared at the same time, though, whereas some competitors do it all at the same time. That might be, okay. Yeah, so why do red then infrared as opposed to red and infrared at the same time? And again, I think I explained that. Our thinking is that you do the red first, then the CCO receptors, they've already been reestablished, so they're not primed to accept another photon of light. So then when the infrared comes by, a lot of those photons, aren't being absorbed by the CCO and the superficial layers because the red's already done its job. Hence, more energy density lower down or deeper down, which is why we do red than near infrared. Thanks for that clarification. Question about PBMT and brain conditions. Yeah, there's tons of research on that, Jade. Just go to PubMed, search PBMT or LLLT and whatever condition you're looking at, Alzheimer's, concussion, or what have you. If the target's cartilage, is that considered a deep tissue? I guess it depends on where that cartilage lies. In the finger joint, it's not that deep. In a knee joint, it's definitely deeper. So definitely if you're trying to get light into the joint cavity, that would be very deep for many joints. How about using heat after photobiomodulation? If it's not an acute inflammatory condition, I think heat is relaxing, helps with blood flow. And in general, we tend to do that at our clinic. And I think it's kind of a nice effect. I don't know if it does a whole lot for photobiomodulation, but if you have time, I think it's good. Patients like it too. So you said more is harmful. So if we want to go deeper, we have to place the laser for a longer time. So it could have harmful effects on the superficial structures. No, again, remember I said that okay, so here's the thing. The light won't affect normal healthy tissue. So you're not going to harm normal healthy tissue. Then the question is, how much light does one need to stimulate the tissue at what depth? And usually you're trying to affect a certain depth or region, but that might be from superficial all the way to deep, which I think is what you're getting at. So if that's the case, then you have to be kind of careful about what you're doing, because you don't want to do too much light on the superficial tissues that are injured or diseased, because they might have a negative effect. So you have to play around with dosaging. It's not an exact science by any stretch of the imagination. I think that's what you're getting at. So I'm going to take a few more questions than in the webinar. If clients with severe conditions such as bulging discs or herniations can only afford to come in weekly, say biweekly, will PBM provide any improvement? Yeah, so that's a good question. I would say this is that a minimum twice a week. If you're doing it once a week, I don't know how much of an effect it will have. Maybe a little bit, but you want to have optimal effect. That's where, Joanne, what I'd recommend is having one or two devices you can rent out to your clients. They treat a little bit at home and they come in for their professional equipment and the laser as well. And then they're getting best of both worlds. And then they can just return the equipment after a month or whatever. They're gotten better. They're still a patient. They're still going to come in or whatever. That might be an option as well. We have a rental program, so you can inquire about that. If wavelength and time are important parameters, does it make any difference if something is laser or LED? No, because light is light. It doesn't matter if it's LEDs or lasers, except that the power density is markedly different. So you have to understand the dosaging. The surface area, which is larger for LEDs, and the power, which is less than lasers, right? So if you take it all in consideration, then you just need to adjust accordingly. If you're treating hip osteoarthritis and using a laser probe, and I've done webinars on this, you probably want to hold it for much longer because you're trying to invoke enough dosage deeper. And, you put the leg in a figure 4 position, you push the probe into the soft tissue anterior joint and try and get it as close to the synovium and the joint capsule as possible. I would say hold it 20 seconds, 30 seconds, maybe 40 seconds. You can play around with that. Oh, here's a good question. Can you get more dosage by kind of sandwiching sort of two arrays at the same time? There was a study on that, and they didn't find any increase like on one side and the other side that you'd actually have greater penetration. They didn't find any effect on that. But what I do recommend is you treat around the circumference of a joint. So if you treat the knee, I would treat all the way around the knee, the joint, which makes sense. For the abdomen, I'm just going to treat over the abdomen, not in the back, because it's not going to get to the abdomen. Yeah, someone's commenting that that twice a week seems to work quite well for them. And like I say, twice a week would be the sort of the sweet spot. 2 to 3 times, I would say. Once a week, I don't think is optimal. But yeah, that's what I would say to that. And last question, I was specifically wondering on the efficacy of devices that are dual applications. Like pads, intranasal, and so forth. I'm not sure what you mean by EG pads. Intranasal is a form of photobiomodulation that tries to get light into the, there's lots of capillaries and blood vessels, and then they're absorbing light, and then that light's carried into the brain. I do not believe for a second that there's much light penetrating through the bone into the brain. Those intranasals, even if they're using laser diodes, they're pretty weak laser diodes, and they're not touching the mucosa. They're reflecting it in, and it's still a distance away. So I think it's BS that any light's going through the skull, like very little. I think it's a systemic mediated effect. Lots of research on that, and you can achieve that by treating around the brain or the brainstem as well. Randy will talk a little bit more about that, the masterclass. Okay, thanks very much for tuning in. That was a long chat. Have a great day, and hopefully we'll see you out at the masterclass. Come and join us. It should be a good time. And let me know if you have any follow-up questions. Email david@bioflexlaser.com. Thanks so much.